In this section of Chapter 10, we're going to talk about the formation of ethers and epoxides. So remember, when we look at our ethers are the oxygen atom that have R groups on either side of them. When we talk about epoxides are three-membered rings with oxygen as one of the members of those rings. And in this group, we're going to look at some different ways that we can form those ethers and epoxides. So one of the ways that we can form these is going to be through a Williamson ether synthesis. In a Williamson ether synthesis, we are going to treat an alkyl halide with the alkoxide anion to generate the ether or potentially the epoxide as well. Through this process, the alkyl halide cannot be tertiary because we're going to undergo an SN2 mechanism. If we had a tertiary alkyl halide, we would end up creating an elimination product instead of the substitution product, instead of the ether that we're going to be looking at. So kind of keep that in mind. We do have some limitations on what that alkyl halide can be to form these ethers. So if we look at our reaction, we are going to be dealing with an alkyl halide. We're going to react that alkyl halide with an alkoxide anion. So remember, that is our RO- unit. And through an SN2 mechanism, we are going to generate then the ether with our halide. Once again, we're going to be very specific with those halides, and those halides can only be chlorine, bromine, or iodine. We are not going to see the use of, again, a fluoro compound for the Williamson ether reaction. To quickly review the SN2 mechanism that we would be looking at, we would generate that alkoxide anion typically in solution. That alkoxide anion is now nucleophilic. It will attack the electrophilic portion of the alkyl halide, driving off the halogen to get us to our final product, which again is the ether that we would be looking for. We can make a wide variety of ethers through this process, including even cyclic ethers if we look at an intramolecular reaction that we looked at in a previous chapter. So now let's look at how we can actually form the epoxide. So remember, that is our three-membered ring. One of the ways that we can form the epoxide is through the use of a halohydrin. A halohydrin specifically is going to be a species that has the alcohol unit and the halogen on adjacent carbon atoms. So specifically, we would be looking at this use of a halohydrin, where we have the halogen and the alcohol on adjacent carbon atoms. Then if we are under basic conditions, we will see epoxides being formed through an SN2 type mechanism. Again, the halogens, we do need to be specific with them. They are going to be chlorine, bromine, or iodine. Again, fluorine is just too reactive that we will not see the use of fluorine as a leaving group through these processes. So again, looking at our mechanism, what we're going to be taking advantage of in our mechanism is going to be an intra reaction. So under our basic conditions, we will deprotonate the alcohol that is on our halohydrin, generating the alkoxide anion there in our compound as well as water. From here, that negatively charged species is going to come in and drive off the halogen in that SN2-like mechanism to get us into our epoxide. So again, specifically using that halohydrin to produce the epoxide species. Another way that we can form our ethers is going to be through the formation of acid-catalyzed reactions of alcohols. Through this acid-catalyzed reaction of alcohols, this is typically how we form symmetric ethers, because we're going to see that the alcohol will react with itself in an intermolecular reaction, meaning we're going to react two of the alcohols together. So through this process, we would have two alcohols. So this is just a stoichiometric coefficient of 2 because they would each react with each other. This is an intermolecular reaction. We would need to be under acidic conditions. So we would end up getting symmetric ethers through the reaction process. This is acid catalyzed, so remember that catalyzed unit means that we start with H3O+, and we should also end with H3O+ as well. This mechanism does occur via both SN1 and SN2 type mechanisms, depending on the level of the alcohol, whether it's primary, secondary, or tertiary. We will see both SN1 and SN2 type mechanisms. So if I walk through the mechanism that I originally had on the screen, we would be dealing with a primary alcohol. So this reaction would take place via the SN2 type mechanism. So under our acid catalyzed conditions, we are going to protonate the original alcohol. From here, our second alcohol unit, which is why we needed 2 of them in our reaction, will come in and behave as the nucleophile, driving off our really good leaving group of water that we generated. That water will then come in and deprotonate our substance to get us back to the neutral ether, as well as regenerating the H3O+ ion that we started with, so our acid catalyzed process. And again, please notice that since we are reacting 2 of the same alcohols together, one alcohol will behave as the electrophile, one of the alcohols will behave as the nucleophile, which is why it is generating symmetric ethers for us.